Begin by watching in full screen, and if future episodes are welcome, subscribe quietly and return later to places where the details begin to matter. The first sensation is not distance, but scale. A sky that is not a ceiling, but a map of options. Each point of light a star with its own history of chemistry and motion. Each star surrounded by a volume of space where rock can gather, ice can condense, gas can swell into envelopes, and heat can be traded between a surface and a sky. The second sensation is time. The realization that the search for a new home is not an event but a measurement, carried out by instruments that do not travel to these worlds but watch them from far away, and infer from faint, disciplined changes in starlight and stellar motion whether another planet exists, how large it might be, how heavy it might be, and whether it inhabits the narrow physical middle ground where liquid water can persist on a surface for geologically meaningful spans of time. Kepler, 22b enters this landscape as a particular kind of object, not the nearest candidate, not the most precisely characterized, not the smallest, not the most Earth-like in every dimension, but among the earliest widely known examples of a planet whose measured size places it in the ambiguous region between rocky super-Earths and volatile rich mini-Neptunes. Orbiting a star similar enough to the Sun that the phrase habitable zone becomes more than an abstract diagram. The name itself is a compression of method and catalog, a planet discovered not by direct image, not by a ship, but by a telescope that stared at a fixed patch of sky and waited for the simplest possible sign of an orbiting body, a periodic dimming. As a planet crosses the face of its star, in that simplest sign lies a deep chain of physics. A transit is geometry before it is biology. It requires a lineup. The plane of the planet's orbit must be oriented so that, from Earth, the planet passes between observer and star. The dimming is small because the star is huge, and the planet blocks only a fraction of the stellar disk. That fraction is a square of the ratio of radii. If the planet's radius is 1/10 the star's radius, the transit depth is about 1%. If the planet's radius is 1/100th, the depth is 10,000ths, and the measurement becomes a contest with noise, with granulation, with stellar spots, with the finite stability of detectors, and with the restless variability of stars themselves. What Kepler measured at its best was a kind of quiet bookkeeping, a time series of brightness values of more than 100,000 stars, each star reduced to a curve, each curve interrogated for repeating patterns that might be the shadow of a planet. The transit provides a radius, not a mass. It yields an orbital period, which, given the star's mass, yields a semi-major axis through Kepler's third law. The rhythm of the dimming becomes the scale of the orbit. For a star like the Sun, a period of about 1 year corresponds to about 1 astronomical unit, the distance between Earth and Sunday Kepler. 22b's period is shorter than Earth's, indicating an orbit closer in an Earth's orbit around the Sun, but still within a region where, under certain atmospheric assumptions, the star's energy could allow surface temperatures compatible with liquid water. This region is not a fixed ring. It is a moving boundary defined by the balance between incoming stellar radiation and outgoing planetary thermal emission, filtered by the absorption spectrum of the atmosphere and reshaped by clouds and surface reflectivity. If the transit is the planet's silhouette, the next question is the planet's weight. Weight determines gravity at the surface. Gravity determines the scale height of the atmosphere, the ease with which gases can be retained against thermal escape, the pressure profile, and the potential for a thick volatile envelope. Gravity influences whether a planet's surface can sustain oceans without losing them to space over billions of years, and whether the planet's interior can maintain convection that drives a magnetic field. In the realm of habitability, mass is not just a number. It is a boundary condition for everything that makes a surface stable, shielded, and chemically active. Mass can be inferred by radial velocity, the slight wobble of the star as it orbits the star-planet barycenter. A star does not sit still. It moves in response to the gravitational pull of its planets. That motion is tiny. For Earth around the sun's reflex motion is on the order of centimeters per second, far below the precision of many instruments for much of modern astronomy. For larger planets, closer planets, heavier planets, the wobble grows. Radial velocity is the measurement of spectral line shifts. The star's light is stretched when it moves away, compressed when it moves toward. Yet stellar atmospheres are not quiet reference frames. Convection moves hot gas upward and cool gas downward. creating line asymmetries. Spots rotate in and out of view, changing the apparent centroid lines. Pulsations shift surfaces. In the case of Kepler, 22b, the star is relatively faint for high-precision radial velocity follow-up, and the planet's longer period and likely moderate mass make the signal difficult. The result is a planet whose radius is constrained by transit, but whose mass is less secure, leading to the central ambiguity that defines Kepler. 22b as a habitability object. It might be a high-mass rocky world with a solid surface, or it might be a lower-density planet with a significant water layer and thick atmosphere. Or it might be a mini-Neptune with a deep volatile envelope and no accessible surface at all. In habitability beyond Earth, this ambiguity is not a footnote. It is a dividing line between a world that could be walked upon and a world that is only a sphere of pressure, where the concept of ground dissolves into a continuum of fluid phases. A planet with a radius around 2.4 Earth radii, as measured for Kepler, 22b, sits near a demographic boundary observed in exoplanet populations, the radius gap or Fulton gap, where planets smaller than roughly 1.5 to 2 Earth radii tend to be denser and likely rocky, while planets larger often retain significant hydrogen-helium envelopes, lowering bulk density and increasing atmospheric scale height. That boundary is statistical, not absolute. Composition depends on formation history, irradiation, and atmospheric loss, but it sets the scientific tone. Kepler, 22b is large enough that the burden of proof shifts. Habitability requires not only a location in the habitable zone, but a surface regime where pressure and temperature permit liquid water, and where a solid crust can participate in long-term carbon cycling. The habitable zone itself must be rebuilt from first principles to remain meaningful. A star emits radiation with a spectrum approximating a blackbody modified by absorption lines and chromospheric activity. A planet at distance receives a flux proportional to the star's luminosity, divided by 4 pi superscript 2. The planet absorbs some fraction of that flux, determined by its bond albedo, and emits infrared radiation according to its temperature and emissivity. If the planet were an airless blackbody, the equilibrium temperature would be set by balancing absorbed and emitted energy. But planets that matter for habitability are not airless. Their atmospheres contain gases that absorb infrared radiation and re-emit it, trapping heat. The strength of this greenhouse effect depends on the concentration of greenhouse gases, the pressure broadening of absorption lines, the vertical temperature profile, and the presence of condensable species, such as water vapor, that can amplify warming through feedback. The habitable zone is therefore an interval of orbital distances where, given plausible atmospheric compositions and pressures, surface liquid water could exist. The inner edge is set by the onset of a runaway greenhouse, where increasing temperature increases water vapor, which increases infrared opacity, which increases temperature further until oceans evaporate and the planet becomes a steam world. The outer edge is set by the limit of greenhouse warming. Beyond a certain distance, even maximal plausible greenhouse gases cannot keep the surface above freezing, and CO2 begins to condense, reducing greenhouse warming. These edges shift with stellar type because the stellar spectrum changes. Cooler stars emit more infrared and red light, which interacts differently with planetary atmospheres and surfaces compared to the sun spectrum. Clouds further complicate the picture by reflecting incoming starlight and trapping outgoing infrared. Cloud feedback can widen or narrow the zone, depending on cloud altitude, particle size, and coverage. Kepler 22 star is a G-type star, not identical to the Sun, but similar enough that solar analog reasoning holds in a first approximation. That similarity matters because a future human habitat is not only about water, but about light and energy. Photosynthesis, if it occurs, would adapt to the spectrum of the star. The thermal environment depends on the spectrum's interaction with atmospheric gases. The star's ultraviolet output affects atmospheric photochemistry, controlling the formation and destruction of ozone, methane, and other molecules that regulate surface conditions and biological exposure to harmful radiation. Within that zone, the planet's own properties dominate. Consider gravity again, now not only as surface acceleration, but as a regulator of atmospheric thickness. A planet with higher gravity can retain lighter gases, particularly hydrogen and helium, the primordial gases of nebulae. If a planet retains a hydrogen-rich envelope, It can develop high surface pressures and temperatures due to the greenhouse effect of hydrogen through collision-induced absorption. This can move the habitable zone outward because hydrogen can trap heat efficiently even in thin concentrations at high pressure. Yet for a planet intended as a human home, a hydrogen-rich envelope is not a straightforward advantage. Hydrogen atmospheres have low mean molecular weight, creating large-scale heights and potentially dynamic, deep atmospheres. The surface pressures could be crushing. The chemical environment could be reducing rather than oxidizing, changing the stability of water, carbonates, and many minerals. Human physiology, dependent on oxygen partial pressure within a narrow range, cannot simply adapt to arbitrary atmospheric compositions. Habitability in an astrophysical sense is not identical to habitability in an anthropocentric sense. A planet can be habitable for life broadly construed, yet still be uninhabitable for humans without technological mediation. The search for a new home is therefore a two-layer question: whether a planet can host stable surface water and long-term chemical cycling, and whether the resulting environment can be engineered or adapted to sustain human life. Kepler, 22 BS radius alone cannot decide. The mass matters, but even mass combined with radius yields only an average density, which can be produced by multiple compositions: an iron-rich core with a rocky mantle, a rocky interior with a deep water layer, a rocky core with a thick hydrogen envelope, mixtures. Planet formation models show that beyond the snow line and a protoplanetary disk, water ice is abundant, and growing planetary embryos can incorporate large fractions of volatiles. Migration can bring such planets inward into the habitable zone, carrying water with them. A planet that forms a substantial water inventory could be an ocean world, with global seas hundreds of kilometers deep. Such a world can have liquid water and moderate temperatures, yet be fundamentally different from Earth in geology. Earth's continents and shallow oceans allow weathering of silicate rocks, drawing down CO2, regulating climate over geological time. A planet with deep oceans may develop a high-pressure ice layer at the bottom of the ocean, separating liquid water from the rocky mantle. If the ocean floor is an ice layer rather than rock, chemical exchange between water and rock is limited, potentially weakening the carbon-silicate cycle that stabilizes Earth's climate. Without that feedback, the climate can drift toward extremes as stellar luminosity changes or as volcanic gases accumulate. Geology must therefore be treated not as scenery, but as a thermostat. Earth's habitability is not solely due to its location. It is due to a feedback system involving plate tectonics, erosion, volcanism, and the cycle of carbon between atmosphere, ocean, and rocks. Plate tectonics is a mechanism for renewing the crust, recycling carbonates into the mantle, and releasing CO2 through volcanism. It also builds continents, creating diverse environments and nutrient flux. Whether plate tectonics occurs depends on planetary size, internal heat, water content, and the rheology of the mantle and lithosphere. Larger planets may have more internal heat and thinner lithospheres, potentially favoring tectonics. But higher gravity increases lithostatic pressure, possibly strengthening the lithosphere. Water acts as a lubricant, reducing rock strength and enabling subduction. A planet can be too dry to subduct. It can also be too in the sense of being an ocean world with insufficient exposed land for weathering. The parameter space is not simple, and Kepler, 22 BS uncertain composition, places it in a range where tectonic behavior could plausibly differ from Earth's in several ways. If tectonics is a thermostat, the atmosphere is the insulation layer that sets how the thermostat operates. Atmospheres are not static. They evolve under stellar radiation, escape, volcanic outgassing, impacts, and biological activity. The initial atmosphere of a planet can be captured from a nebula dominated by hydrogen and helium. If that envelope is lost through photoevaporation driven by high-energy photons, the planet may be left with secondary atmospheres generated by outgassing of volatiles trapped in the mantle. Secondary atmospheres include CO2, H2O, N2, SO2, and other gases. The eventual composition depends on redox state, volcanic flux, and surface sinks. Nitrogen is often a background gas, important not as a greenhouse gas, but as a pressure buffer that broadens absorption lines of greenhouse gases and supports liquid water by raising surface pressure. Oxygen, crucial for humans, is not typically produced abiotically in large quantities under stable conditions, though photolysis of water followed by hydrogen escape can leave oxygen behind. But oxygen can also be consumed by surface reactions, so sustained high O2 levels likely require biological production or an unusual combination of sinks and sources. In this frame, a potential human home requires either an atmosphere that already contains oxygen at usable partial pressures or an atmosphere that can be transformed. Terraforming is a word that tends to encourage loose imagery, but as a physical process, it is a balance of mass budgets and timescales. How many kilograms of oxygen are needed to produce breathable partial pressure over the entire surface? What energy is required to produce it? How quickly would it be consumed by oxidation of surface minerals? How would it be retained against escape? On a world with higher gravity, oxygen is easier to retain, but creating it remains chemically expensive. The problem is not only oxygen, it is the total atmospheric pressure, the presence of toxic gases, and the thermal regime. A planet with high CO2 pressure might have surface temperatures too high and air too dense. A planet with low pressure might have water that boils or sublimates. Kepler 22b stellar insolation suggests, under some models, a relatively temperate equilibrium temperature, but equilibrium temperature is only a baseline. The real surface temperature depends on greenhouse warming and clouds. If Kepler 22b has a thick atmosphere, cloud decks could increase albedo and cool the surface, potentially allowing a planet receiving more energy than Earth to remain temperate. Conversely, if the atmosphere has strong greenhouse gases, it could become hot even at moderate insolation. The possibility space includes states reminiscent of Venus, Earth, or something intermediate, and the challenge is that current observations provide few constraints on atmospheric composition. The next layer of inference comes from transit spectroscopy. During a transit, a small fraction of starlight filters through the planet's atmosphere at the limb. Molecules absorb at specific wavelengths, imprinting spectral features that can reveal composition. The strength of features depends on the scale height of the atmosphere, which depends on temperature and mean molecular weight and gravity. Hydrogen-rich atmospheres produce large features, easier to detect. High mean molecular weight atmospheres, dominated by N2, CO2, H2O, produce smaller features, harder to detect. Clouds and hazes can mute features by creating a high-altitude opaque layer, making the atmosphere appear flat in transmission. For Kepler 22b, the host star's brightness and the planet's parameters make such spectroscopy challenging, but the principle is central. To judge habitability, it is not enough to know a planet exists in a certain orbital band. The atmosphere must be characterized, and atmospheric characterization is intertwined with planetary gravity and composition. Even when atmospheric gases are detected, interpreting them in terms of habitability is non-trivial. Water vapor indicates the presence of water somewhere, but not necessarily a surface ocean. It can exist in steam atmospheres. CO2 indicates greenhouse capacity and a source from outgassing, but CO2 can also dominate in uninhabitable hot states. Methane can be biological or geological. Oxygen can be biological or photochemical. Ozone is a photochemical product of oxygen and can indicate oxygen presence. But these molecules must be interpreted in context, including the star's UV spectrum, the planet's temperature, and the presence of sinks. A future human habitat is, in effect, a planet where the surface is accessible and stable, where radiation is manageable, where gravity is within tolerable ranges, where atmospheric pressure and composition are compatible with human physiology or could be made so, and where resources are available: water, carbon, nitrogen, metals, energy. Resources are not just about abundance, but about availability. Water locked beneath ice is different from water in oceans. Nitrogen locked in rocks is different from nitrogen in an atmosphere. Carbon locked in carbonates is different from carbon in an atmosphere. A planet can be rich in elements and still be impractical if those elements are trapped in inaccessible forms. Gravity deserves revisiting from this human-centered angle. Human physiology evolved under 1G. Long-term exposure to lower gravity affects bone density, muscle mass, cardiovascular function. Higher gravity imposes chronic load, potentially affecting heart function, mobility, and reproduction. A planet with radius 2.4 Earth radii could have surface gravity significantly higher than Earth if it is rocky and massive, perhaps 1.5 G or more depending on mass-radius relation. If it is volatile rich with lower density, surface gravity might be closer to Earth's. Without mass, the uncertainty is wide. The difference between a manageable 1.1 g and a difficult 1.8 g is not a detail. It is an environmental constant that shapes every movement, every engineering design, every biological adaptation. Even architecture changes. Structures must support more weight. Flight becomes more demanding. Atmospheric scale height shrinks under higher gravity, affecting weather and the vertical distribution of gases. But gravity also shapes atmospheric retention and climate. A higher gravity compresses the atmosphere, potentially increasing surface pressure for a given atmospheric mass. Increased pressure broadens absorption lines, enhancing greenhouse effect for gases like CO2 and H2O. Pressure also increases the boiling point of water, allowing liquid water at higher temperatures. Yet high pressure can also make breathing difficult, and high partial pressures of oxygen can become toxic. A human-compatible atmosphere is a delicate mix. Total pressure and oxygen partial pressure must be balanced to avoid hypoxia or oxygen toxicity. Nitrogen narcosis occurs at high pressures, and decompression sickness becomes a hazard if living environments differ from outside conditions. These physiological constraints tie planetary atmospheric physics directly to habitability for humans. Radiation is another constant. A planet in the habitable zone of a sun-like star receives not only visible light, but UV and energetic particles. The planet's magnetic field, atmosphere, and surface environment determine how much radiation reaches the ground. Earth's magnetic field deflects charged particles from the solar wind, reducing atmospheric stripping and protecting the surface from radiation events. The atmosphere itself, especially ozone, absorbs harmful UV. On a planet without a magnetic field, stellar wind can erode the atmosphere over time, especially for planets close to active stars. But for a planet at Kepler, 22 BS orbital distance around a sun-like star, the stellar wind pressure is lower than for close-in planets, potentially making atmospheric retention easier even without a strong magnetic field. Yet without a magnetic field, high-energy particles can still penetrate the upper atmosphere, driving chemistry and potentially creating auroral ionization and radiation belts. The generation of magnetic field depends on a conducting fluid region in the interior, such as a liquid iron core, and sufficient convection to sustain a dynamo. Convection is driven by heat loss in the core and by compositional buoyancy as the core solidifies. Planetary size affects cooling rate. Larger planets cool more slowly, potentially sustaining liquid cores longer. But if a planet is too large and retains too much heat, the core may not cool enough to convect vigorously, weakening the dynamo. The presence of plate tectonics affects mantle convection and heat loss. Thus, magnetic protection is linked to geology. An ocean world with an insulating high-pressure ice layer might have different heat transfer properties, potentially affecting dynamo behavior. Kepler, 22 BS unknown composition again matters. A rocky world with an iron core could have a dynamo. A volatile-rich mini-Neptune with deep layers of water and high-pressure ices could have magnetic fields generated in ionic water layers or other conducting regions, producing different field geometries and strengths. For human habitation, what matters is the integrated radiation environment at the surface. A thick atmosphere can provide shielding even without a magnetic field, especially if the atmosphere is dense enough to stop energetic particles. But thick atmospheres also imply high surface pressures and potential greenhouse warming. A thinner atmosphere might be breathable but offer less shielding, requiring technological protection. Thus, radiation and atmospheric pressure trade-off. Orbital mechanics enters not as a mathematical sidebar, but as a long-term stability question. A planet's climate stability depends on the stability of its orbit and rotation. The eccentricity of the orbit determines seasonal variation in stellar flux. Earth's orbit is nearly circular, but even modest eccentricity can create strong variation affecting climate. The obliquity or axial tilt determines seasonal distribution of sunlight. Earth's obliquity is stabilized by the moon, preventing chaotic swings that could destabilize climate. Without a large moon, a planet's obliquity can vary chaotically due to gravitational interactions with other planets, potentially driving extreme climate variations. The presence of a moon also drives tides, mixing oceans, influencing coastal environments, and possibly aiding in prebiotic chemistry and early evolution. For human habitability, tides matter less than for origin of life scenarios, but ocean mixing and climate may still be relevant. A large moon also affects rotation rate over time, slowing it through tidal friction. Kepler, 22 BS moons, if any, are unknown. Detecting exomoons is difficult. It requires observing subtle variations in transit timing and duration or direct photometric signatures. The absence of evidence is not evidence of absence. Yet for a multi-hour documentary grounded in science, the role of moons can be treated as conditional. If a planet like Kepler 22b lacks a large stabilizing moon, obliquity variations could be larger. If it has one, stability could be enhanced. These conditional branches are not speculation as narrative ornament. They are physics scenarios that shape long-term climate. Rotation rate and tidal forces also matter. Planets close to their stars can become tidally locked, presenting the same face to the star, producing permanent day and night hemispheres. Tidally locked planets around red dwarfs are common because habitable zones are close in. Kepler 22b, orbiting a sun-like star at a moderate distance, is less likely to be tidally locked, though tidal evolution depends on internal dissipation and the system's age. If it is not locked, it may have a day-night cycle, which can support atmospheric circulation patterns similar to Earth's. If it were locked, atmospheric dynamics could still redistribute heat, but the climate will be structured around a permanent substellar point and a permanent night side, with possible cold traps for volatiles. For a human habitat, a non-locked planet offers more Earth-like diurnal cycles, but locked planets might still be habitable with sufficient atmosphere and ocean heat transport. The subject expands beyond Kepler, 22b not by leaving it behind, but by placing it among neighbors in parameter space, planets discovered by Kepler and later missions that occupy similar radii, similar insolation, similar stellar types. Each comparison sharpens the inference. Planets like Kepler 452b, another candidate around a sun-like star with longer period, are often discussed in the same breath, but each has its own observational uncertainties. Planets like those in the TRAPPIST, one system illustrated a different regime. Small planets around a cool star, with intense stellar activity and likely tidal locking. They are not directly analogous to Kepler 22b, but are essential to understanding the broader constraints of habitability. The distribution of exoplanets shows that Earth-sized planets exist, but the most common are intermediate sizes, super-Earths and mini-Neptunes. This tells something about formation and atmospheric retention. Nature produces many worlds that are not Earth analogs, and the problem of finding a human home may be less about finding a planet at the right distance and more about finding one with the right composition and evolution. Evolution is a hidden variable in habitability. A planet's present state depends on its history. Initial composition impacts migration, stellar evolution, atmospheric loss. A planet can begin with thick hydrogen and later lose it, exposing a rocky core. It can begin with abundant water and later lose it through photolysis and hydrogen escape. It can begin dry and later receive water through impacts. The star evolves too. Sun-like stars brighten over time as hydrogen is fused into helium in the core, increasing luminosity. Over billions of years, the habitable zone moves outward. Earth's climate has remained habitable partly because carbon cycling adjusts atmospheric CO2 to compensate for increasing solar luminosity. A planet like Kepler 22b, if older, might have experienced a different luminosity history and might now sit in a different climate regime than it did in its past. A planet can be in the habitable zone and still be too hot if its atmosphere is thick and its star is brightened. The scientific exploration of these worlds depends on measuring stars as carefully as planets. Stellar radius determines planetary radius from transit depth. Stellar mass determines orbital distance from period. Stellar age determines evolutionary state. Stellar metallicity influences planet formation. Higher metallicity tends to produce more giant planets, but the relationship for smaller planets is subtler. Stellar activity influences atmospheric escape and photochemistry. Thus, a planet's habitability is often limited by uncertainties in stellar properties. Kepler's original target stars were characterized through photometry and spectroscopy, but many have uncertainties. Later missions and surveys refined these values. The more precise the star, the more precise the planet. The process of measuring a planet like Kepler 22b is therefore iterative, not definitive. A transit yields a candidate. Validation requires ruling out false positives, such as eclipsing binaries or background blends. The Kepler pipeline performs statistical vetting, but confirmation can require multiple lines of evidence. Once confirmed, characterization proceeds with radial velocity, transit timing variations, and eventually atmospheric spectroscopy. Each step is constrained by instrument sensitivity and by the star's brightness. This instrumentation is part of the story because habitability is, in practice, an inference problem. A future human home beyond Earth cannot be evaluated without turning photons into physical parameters. Photons carry information about a planet's size, atmosphere, temperature, and sometimes surface conditions. But photons are scarce. A planet is faint, its atmosphere thinner still. The available information is filtered through noise and models. Therefore, scientific grounding requires constant awareness of what is measured and what is inferred. Kepler 22b's measure radius is a measurement. Its composition is an inference uncertain. Its surface conditions are a model outcome, contingent on assumptions. In a grounded narrative, the uncertainty is not treated as ignorance, but as a parameter range. Within that range, scenarios could be explored. One scenario where Kepler 22b is a rocky super-Earth with a moderate atmosphere, another where it is an ocean world, another where it is a mini Neptune. In the rocky super-Earth scenario, the planet has a solid surface. Its gravity may be higher than Earth's, affecting atmosphere and human physiology. Its mantle may be active, potentially supporting volcanism and tectonics. Volcanism would replenish atmospheric gases and provide nutrients. If plate tectonics exists, carbon cycling could stabilize climate. The atmosphere might be composed of N2 with CO2 and water vapor, potentially similar to early Earth or modern Earth depending on biological evolution. Oxygen would likely require life. Without oxygen, human habitation would require sealed habitats or atmospheric modification. Surface water could exist as oceans, lakes, rivers, depending on topography and climate. In the ocean world scenario, the planet's bulk density is lower, indicating large water content. Surface might be global ocean. Land could be absent or minimal. Weathering might be limited. Climate stability might rely on different feedbacks, perhaps involving ocean atmosphere chemistry and cloud dynamics rather than continental weathering. Nutrient cycling might be constrained by limited rock-water interaction. Yet a global ocean could be stable, and human habitats could be floating or underwater. But such designs shift the meaning of new home from open-air settlement to engineered environments. The availability of metals and minerals would depend on access to seafloor and crust. High pressure at depth would create exotic ice phases, changing ocean circulation. In the mini-Neptune scenario, the planet retains a thick hydrogen-helium envelope. The pressure at any hypothetical surface would be immense, and temperatures could be high. There might be no solid surface accessible. The planet would not be a candidate for open-air human habitation. It could still be scientifically interesting and possibly habitable in the sense of having temperature-pressure regions where liquid water could exist, perhaps in layers, but not as a human home in the straightforward sense. Determining which scenario applies requires mass measurement and atmospheric characterization. Mass from radial velocity is difficult, but not impossible with advanced spectrographs and long observing baselines. Alternatively, transit timing variations can yield mass if multiple planets interact gravitationally, causing variations in transit times. If Kepler 22b had nearby planets, TTVs could help. In many systems, TTVs are powerful for determining masses of small planets, particularly in compact multi-planet systems. The presence or absence of TTV signals itself reveals architecture, whether the system is dynamically packed. Architecture matters because it affects orbital stability and potentially impact rates. Planetary systems can be quiet or chaotic. A quiet system with stable orbits can allow long-term climate stability. A chaotic system with frequent perturbations can increase eccentricity and obliquity changes, and can increase impact rates, potentially resetting atmospheres. Impacts can deliver volatiles, but large impacts can also strip atmospheres and sterilize surfaces temporarily. Over geological time, a balance exists. Enough impacts to deliver water and organics early, but not so many that life cannot persist. 4. Kepler. 22b. The system's full architecture is not fully mapped, but the star's properties and the planet's presence suggest formation in a disk that could have produced additional planets. Future surveys and reanalysis can detect additional transiting planets or non-transiting companions through radial velocity trends. Each additional planet will refine the dynamical context. The star spectral type also defines the long-term radiative environment. Sun-like stars have relatively stable luminosity on main sequence, but they have activity cycles and flares. Their UV output is moderate compared to M dwarfs, but still significant. For planetary atmospheres, high-energy photons drive escape by heating the upper atmosphere and causing hydrodynamic outflow. Hydrogen escapes most readily. This can remove primordial envelopes, potentially converting mini Neptunes into rocky super-Earths. Thus, the star can sculpt the planet population. For planets in the habitable zone around Sun-like stars, the high-energy flux is lower than for closed-in planets, making atmospheric retention more likely. But early in a star's life, its high-energy output can be higher. Early irradiation can strip atmospheres before the star settles. Planetary atmosphere escape is a physical process with multiple regimes. Genes escape, where individual molecules in the tail of Maxwell-Boltzmann distribution exceed escape velocity. Hydrodynamic escape, where the upper atmosphere behaves like a fluid outflow, carrying heavier species with it. Non-thermal escape processes such as sputtering and ion pickup. Escape depends on temperature, gravity, composition, and magnetic interactions. A planet with higher gravity resists escape. A planet with strong UV radiation is more vulnerable. In the context of habitability, escape can be beneficial if it removes a thick hydrogen envelope, exposing a potentially habitable surface. But escape can be harmful if it removes water and leaves a desiccated world. Water loss through photolysis is a key habitability hazard. In a runaway greenhouse, water vapor reaches the upper atmosphere, where UV photons split into hydrogen and oxygen. Hydrogen escapes. Oxygen accumulates or reacts with surface minerals. Over time, oceans can be lost. Therefore, being near the inner edge of the habitable zone can be dangerous, depending on cloud feedback and atmospheric composition. A planet like Kepler, 22b may receive similar or slightly less flux than Earth depending on stellar parameters, but the uncertainty in albedo and greenhouse effect means its actual climate could range from temperate to hot. Climate itself must be treated as a dynamical system. Atmospheres transport heat by winds. Oceans transport heat by currents. The distribution of continents affects circulation. The rotation rate influences Coriolis forces, shaping jet streams and storm tracks. A planet with a higher mass might rotate faster or slower, depending on formation and tidal evolution. Rotation influences the width of Hadley cells and the efficiency of heat redistribution. A planet with slow rotation might have fewer, broader circulation cells, potentially reducing temperature gradients. Clouds form in response to convection and surface evaporation. Cloud cover can increase reflectivity and cool the planet, but can also trap heat depending on altitude and optical properties. Cloud feedback is among the largest uncertainties in habitable zone calculations. On Earth, low clouds cool, high cloud warm. The net effect depends on their distribution. For exoplanets, cloud patterns could differ. On a planet with higher insolation, increased convection could create thick reflective clouds on the day side, potentially stabilizing temperature. Some models suggest that slowly rotating planets can develop thick substellar cloud decks that extend habitability inward, yet such outcomes depend on microphysical assumptions. For Kepler, 22b, without direct measurements, climate models offer plausible regimes rather than predictions. Even if surface temperatures permit liquid water, the chemistry of the ocean matters. Ocean pH, salinity, and composition affect the solubility of gases like CO2 and O2 and the availability of nutrients. Earth's ocean chemistry is tied to geological and biological processes. On an exoplanet, ocean chemistry could be different. A planet with high CO2 outgassing could have acidic oceans. A planet with limited rock interaction could have low nutrient availability. For human habitation, ocean chemistry matters for agriculture, water treatment, and ecosystems. A world with accessible fresh water is different from a world where water is global but highly saline or chemically harsh. The concept of future human habitat, therefore, needs to remain grounded in environmental parameters, not in imagery. A home is a system: breathable air, drinkable water, manageable temperature, shelter from radiation, stable ground, and access to materials for building and sustaining technology. In planetary terms, that translates into a planet with a stable atmosphere, a surface that is neither too hot nor too cold, a radiation environment that is not lethal, and resources that can be extracted. If the natural environment is not directly compatible, then a home becomes a network of habitats, sealed and supported by local resources. The boundary between a planet that is habitable and a planet that can be colonized is therefore one of engineering scale and energy cost. Energy is not optional. On Earth, energy comes from solar radiation and from chemical energy stored in fuels. On another planet, solar energy depends on stellar flux and atmospheric transparency. Nuclear energy depends on availability of fissile materials, which depends on planet's geology. Geothermal energy depends on internal heat. Wind and tidal energy depend on atmospheric density, rotation, and moons. A planet with thick atmosphere could support powerful wind energy. A planet with thin atmosphere might not. A planet with slow rotation might have different wind regimes. Kepler, 22 BS distance from Earth is large, meaning direct exploration is not currently feasible. Therefore, the only way to evaluate it as a potential home is through remote sensing and comparative planetology. Comparative planetology uses a diversity of planets to infer relationships between properties. For example, the relationship between radius and density in known exoplanets helps infer whether a planet of given radius is likely rocky. The relationship between incident flux and radius distribution helps infer atmospheric loss. The relationship between stellar type and planet occurrence helps prioritize targets. In this context, Kepler 22b represents an early anchor in the category of potentially temperate super-Earth/mini Neptune candidates. Its importance is not only its own characteristics, but the way it forced the habitability discussion to confront intermediate-sized planets, which may be more common than Earth analogs. If the most accessible habitable worlds are not Earth-sized, then human habitation might involve higher gravity and different atmospheres, and the engineering challenge becomes central. To keep the narrative scientifically grounded, every revisit to Kepler, 22b must attach to the physics that can be inferred. The planet's radius suggests certain gravity ranges. Its orbital period suggests certain insolation. Its host star suggests certain spectrum and activity. Together, these define a set of climate model inputs. Without mass and atmospheric data, the output remains a probability distribution. The scientific process then becomes an incremental tightening of that distribution. Future telescopes with improved sensitivity can measure radial velocities of fainter stars. Transit spectroscopy with large space telescopes can detect atmospheric features of smaller planets, though the feasibility depends on star brightness and planet size. Direct imaging, using coronagraphs or star shades, can separate planet light from star glare, allowing reflection spectra that reveal clouds, surface types, and atmosphere composition. Direct imaging is easier for planets farther from their stars and for nearby systems. Kepler 22b is far, but the method is central to long-term search for new homes. Direct imaging introduces another foundational concept: phase curves. As a planet orbits, the visible illuminated fraction changes. Measuring the combined light can reveal albedo, atmospheric circulation, and temperature distribution. Thermal phase curves in infrared can reveal day-night temperature differences. For a non-tidally locked planet, the phase curve reflects seasonal variations. For a tidally locked planet, it reflects heat transport. Again, for Kepler 22b, Such measurements are beyond current capabilities, but understanding them is necessary because they represent the path from planet detection to climate characterization. The narrative can remain continuous by letting the physics deepen, from transit depth to radius, from radius to gravity, from gravity to atmosphere, from atmosphere to climate, from climate to geology, from geology to long-term stability, from stability to human physiology and resource use, from resource use back to observational constraints. Each loop tightens a connection to the central question: can a world like Kepler 22b or a world in the same class become a new home? In the background, Earth serves not as a sentimental reference but as an empirical case study. Earth's habitability emerges from its position, its atmosphere, its oceans, its geologic cycles, and its magnetic field. Earth shows that being in a habitable zone is not sufficient. Venus is near the inner edge and is uninhabitable at the surface due to runaway greenhouse. Mars is near the outer edge and is cold and thin air due to atmospheric loss and weak greenhouse. These neighbors define failure modes: too much greenhouse, too little atmosphere. For exoplanets, these modes remain. A planet like Kepler 22b might avoid them or fall into them depending on its evolution. The greenhouse effect must be revisited with more specificity because it determines whether habitable zone placement translates into actual habitability. Greenhouse warming arises from gases that absorb infrared radiation at wavelengths where the planet emits. CO2 has strong bands near 15 microns, with wings that broaden with pressure. Water vapor absorbs across many bands, including rotational bands in the far infrared. Methane absorbs in mid-infrared. The overlap of absorption bands and the atmospheric temperature profile determine the outgoing long-wave radiation limit. In a runaway greenhouse, outgoing radiation reaches a ceiling. Adding more water vapor does not increase outgoing radiation because the atmosphere becomes opaque and the emission level rises to high altitude, where temperature is constrained. Once incoming flux exceeds this limit, the planet cannot radiate enough energy to balance, and surface temperature rises until oceans evaporate. On the other side, CO2 greenhouse can warm a planet by absorbing infrared, but at high concentrations and low temperatures, CO2 can condense, reducing greenhouse effect, and scattering can increase albedo. The outer edge is determined by maximum greenhouse. Beyond that, even high CO2 cannot keep surface above freezing. Yet additional gases like hydrogen can extend habitability by collision-induced absorption, and clouds of CO2 ice can reflect or trap heat depending on microphysics. For a planet larger than Earth, the atmospheric column mass for a given surface pressure is different because gravity differs. Surface pressure equals weight of the atmospheric column per unit area P equals G asterisk column mass. For higher G, the same column mass yields higher pressure. For a given outgas mass, pressure is higher. Thus, a larger planet with more G could develop higher pressures more easily, potentially intensifying greenhouse effects. But higher pressure also supports liquid water stability. This interplay becomes critical in assessing whether a super-Earth in a habitable zone is more likely to be a super-Venus or a stable temperate world. Some theories suggest that super-Earths might be more likely to retain thick atmospheres and become hot if near inner edge. Others suggest that increased gravity can suppress water loss by reducing scale height and diffusion of hydrogen, and that a larger planet might retain more water. The outcomes depend on initial water inventory, atmospheric composition, and stellar history. Kepler, 22b's insolation, if comparable to Earth's or slightly lower, could place it within a stable region if greenhouse is moderate. But if it has high CO2 or thick atmosphere, it could be warmer. If it has reflective clouds, it could be cooler. Without atmospheric data, the range persists. Biological constraints add another layer of specificity. Life as known requires liquid water, but also requires a solvent with suitable properties: polarity, ability to dissolve ions, high heat capacity, and a temperature range compatible with complex chemistry. Water meets these. But life also requires energy gradients. Redox couples light geothermal. It requires nutrients: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, trace metals. On Earth, nutrient cycles are driven by geology and biology. On an exoplanet, nutrient availability depends on rock composition and weathering. A planet with no exposed land might have limited phosphorus supply, which comes from weathering of rocks. Without sufficient nutrients, biospheres might be sparse, affecting atmospheric biosignatures like oxygen. For human habitation, the presence of the biosphere could help by producing oxygen and stabilizing environment, but could also introduce pathogens or ecological complexities. Yet a biosphere is not assumed. The focus remains on whether the planet can physically support a stable environment. Oxygen for humans might need to be produced technologically regardless. The detectability of biosignatures is tied to habitability because it provides indirect evidence of surface conditions. Oxygen and methane in disequilibrium could suggest life, but false positives exist. High oxygen could result from water loss. Methane could be geological. Therefore, biosignature interpretation requires context, stellar UV, planetary mass, and atmospheric composition. For a planet like Kepler 22b, if oxygen were detected, it would be a profound clue, but interpretation would require understanding whether the planet could have lost water and accumulated oxygen without life. This returns to the importance of measuring not only one molecule but an ensemble. CO2, H2O, O2, O3, CH4, CO, N2, often inferred indirectly, and temperature structure. The combination reveals redox state and atmospheric processes. Even a human habitat without an Earth-like biosphere could be viable if the physical conditions are stable. Stability implies that climate does not oscillate wildly. Earth has glacial cycles driven by orbital variations, Milankovitch cycles, modulated by feedbacks. A planet with different obliquity or eccentricity could have stronger cycles. If Kepler 22b has higher gravity and thicker atmosphere, heat capacity of the atmosphere could damp temperature swings. Oceans also damp swings. A deep ocean world could have high thermal inertia, smoothing climate. Yet deep oceans can also produce high humidity and clouds, affecting albedo. If the planet is warm, water vapor could dominate, pushing toward greenhouse. But cloud albedo could counteract. The net effect depends on circulation. In a continuous documentary narration, the attention can remain on the physics of inference and the physical prerequisites of habitability, using Kepler 22b as a recurring coordinate. Each revisit can sharpen a different constraint: gravity, atmosphere, geology, magnetic field, orbital stability, and human physiology. The concept of surface itself must be handled carefully for planets of this size. A surface, in a scientific sense, is where pressure and temperature place matter in condensed phase, and where a boundary exists between solid and fluid. For mini-Neptune, there may be no solid surface accessible. The surface is a pressure level where optical depth becomes large. For a rocky world, surface exists. For an ocean world, surface is ocean-air interface, but the rock-water interface is deep. For human habitation, surface must support structures. Floating structures are possible, but require materials. Materials require access to crust. Thus, a planet with some land fraction is advantageous. Land fraction depends on topography and water volume. Earth's water volume covers 70% of the surface, but leaves continents. An ocean world with 10 times Earth water could drown continents. Kepler 22b's possible water content is unknown. Planetary radius affects internal pressure. Larger planets have higher pressures at depth, affecting mineral phases and mantle dynamics. This influences volcanic degassing. If a planet's mantle is under higher pressure, melting might occur at different depths and compositions. Volatile solubility in magma increases with pressure. Deep volcanism might retain volatiles rather than releasing them. Thus, outgassing could differ, affecting atmosphere formation. A larger planet could have a thicker atmosphere if outgassing is efficient. But if volatiles remain trapped, atmosphere could be thinner. Again, uncertainty. The star's metallicity affects planet composition and formation. Higher metallicity disks can produce more solids, perhaps leading to larger cores that capture gas. Kepler 22's metallicity can be measured spectroscopically. That value influences the probability that Kepler 22b formed with a significant envelope. If metallicity is high, gas capture might be more likely, but the relationship is probabilistic. Another essential constraint is the planet's temperature-pressure profile, and the phase diagram of water. Water has multiple ice phases at high pressure. At pressures above roughly 1 GPa, water forms ice 6 and 7 at temperatures where ordinary ice would melt at low pressures. In deep oceans, bottom pressure can exceed these values, creating ice layers even if temperature is warm. This can isolate ocean from rock. For habitability and for human use, isolation matters because it limits nutrient flux. It also limits access to crust for mining. Therefore, a planet's size and water volume can create a regime where the ocean is thick enough to generate high-pressure ice at depth. If Kepler 22b is large and water-rich, this is plausible. If it is mostly rocky with modest water, it might have shallow oceans and exposed land. Without mass, neither can be ruled out. A further layer, atmospheric circulation on larger planets. Scale height h equals kT/μg. For higher g, h is smaller, meaning the atmosphere is more compressed. This can affect the vertical mixing of gases, the tropopause height, and cloud formation. It also affects the altitude at which ozone forms and the shielding of UV. Weather patterns might be more intense due to higher pressure gradients, but also depend on rotation. The star's luminosity and spectrum determine photochemistry. In a sun-like spectrum, ozone can form from oxygen. In low UV environments, ozone might be weaker. Ozone provides UV shield. For human habitats, UV exposure matters. It affects skin cancer risk, DNA damage, and ecosystem stability. If a planet lacks ozone but has thick atmosphere, UV might still be attenuated by Rayleigh scattering and other absorbers. CO2 absorbs UV at certain wavelengths. Hazers can absorb. The net surface UV environment can vary widely. Cosmic rays and stellar energetic particles can penetrate atmospheres and create secondary radiation. Thick atmospheres shield more. Magnetic fields deflect charged particles, but not neutral cosmic rays. Therefore, atmospheric thickness is primary. On Mars, thin atmosphere provides little shielding. On Earth, thick atmosphere provides strong shielding, making surface radiation manageable. A future human home benefits from a thicker atmosphere, but pressure must remain within physiological limits or habitats must be pressurized differently. The interplay between pressure and oxygen partial pressure can be engineered. Humans can live at lower total pressure if oxygen fraction is higher, as in spacecraft atmospheres, but fire risk increases. Conversely, higher pressure with lower oxygen fraction can be safe, but breathing density increases work of breathing. Thus, if a planet's natural atmosphere has total pressure higher than Earth but oxygen fraction lower, breathable partial pressure might be possible, but other gases might be problematic. All of these considerations are not diversions. They're the physical constraints that define whether Kepler 22b-like planets can serve as future homes. From the observational side, one can revisit the limitations of transit method. Transit yields radius, but depends on stellar radius. It favors planets in edge-on orbits. It is biased towards short periods because more transits occur during observation time. Kepler's mission duration allowed detection of longer period planets, but detection completeness drops with period. Therefore, the catalog of habitable zone planets around sun-like stars is incomplete and biased. Kepler 22b's detection was possible because it transited during the mission and had sufficient signal-to-noise. This bias affects the statistics of potentially habitable planets. The occurrence rate of Earth-sized planets in habitable zones, often called Eta Circle Plus, is estimated with uncertainties. For future human habitats, the relevant occurrence rate includes not only Earth-sized but also super-Earths with suitable atmospheres. The number of candidate worlds may be large, but characterization remains difficult. As instrumentation improves, the search shifts to nearer stars because near targets allow better follow-up and potential future direct imaging. Missions like TESS focus on bright nearby stars, finding planets that can be characterized with ground-based radial velocities and future space telescopes. Kepler focused on a distant field, providing statistics. Kepler 22b is part of that statistical foundation. It may not be the first target for detailed characterization, but it remains a reference in the development of habitability science. This creates a subtle but important implication. The planets that first appear promising as human homes might not be the ones most famous or earliest discovered, but those around nearby stars where data can be rich. Yet Kepler 22b remains central as a conceptual archetype, a temperate candidate in the super-Earth/mini-Neptune regime. Understanding it means understanding an entire class of worlds that may be common. The class is sometimes called sub-Neptunes or mini-Neptunes. Their habitability is debated. Some may have thick atmospheres and no surfaces. Others may be rocky cores with moderate atmospheres. The distinction may depend on atmospheric loss. Planets receiving higher flux can lose envelopes, leaving rocky cores, creating super-Earths. Planets receiving lower flux retain envelopes. Therefore, in the habitable zone, envelope retention is more likely, meaning many habitable zone planets of 2 to 3 Earth radii might be volatile-rich. If so, Earth size may be more likely to be rocky, but Earth-sized planets are harder to detect and characterize. This shapes the practical search for human homes. It may be easier to find and measure planets that are slightly larger, but those may be less likely to have accessible surfaces. An additional layer is the role of atmospheric composition in surface habitability on super-Earths. A planet with a hydrogen-rich envelope can, in principle, have temperate conditions at certain pressures and temperatures, and hydrogen can act as a greenhouse. Yet the surface pressure might be too high for humans. But if the planet has a shallow hydrogen envelope, perhaps tens of bars, conditions could be engineered in floating habitats at certain altitudes where pressure and temperature are Earth-like. This is an idea grounded in physics. In a thick atmosphere, there can exist a level where pressure is 1 bar and temperature is moderate, even if the lower atmosphere is too dense and hot. This resembles the concept of aerostat habitats in Venus's atmosphere. On a mini-Neptune, similar could exist, but this is not a simple new home in open air. It is habitation in a layer of atmosphere. The feasibility depends on atmospheric composition, stability, and dynamics. Hydrogen atmospheres have low density, affecting buoyancy. Breathing oxygen in a hydrogen-rich environment is dangerous due to flammability, requiring strict separation. These are engineering constraints tied directly to planetary physics. They do not drift into fiction because they depend on pressure and buoyancy relations. Buoyant force depends on density difference between lifting gas and surrounding gas. In CO2 atmospheres, nitrogen-oxygen mixtures are buoyant. In hydrogen atmospheres, almost nothing is buoyant except vacuum structures or heated hydrogen, making aerostat habitats difficult. Therefore, the composition of the atmosphere defines possible habitation strategies. If Kepler 22b is a mini-Neptune with hydrogen, aerostat habitats might be difficult. If it has CO2 or N2, aerostats could be easier. If it has Earth-like composition, surface habitation is possible. The uncertainty in composition therefore translates into qualitative differences in settlement strategy. Returning to first principles of planetary formation can constrain likelihood. Planets form in disks of gas and dust. Dust grains collide and stick, forming planetesimals. Planetesimals accrete into embryos. Gas giants form when cores exceed a critical mass and accrete gas rapidly. Smaller planets may capture some gas, but not run away. The amount of gas captured depends on core mass and disk conditions. A planet with radius 2.4 Earth radii suggests a core mass, perhaps several Earth masses. Such a core could capture a substantial envelope if it formed early. If it formed late, after disk dissipated, envelope could be small. Migration can move planets inward, but migration timescales depend on disk properties. A planet in the habitable zone could have formed there or migrated. If Kepler 22b formed beyond the snow line, it could have accreted water-rich material and then migrated inward, becoming an ocean world. If it formed near current orbit, it might be less water-rich. This model suggests that many super-Earths migrate, but statistical patterns also show many close in super-Earths. The habitable zone around sun-like stars is farther out, where disk density is lower, potentially slowing growth. Therefore, forming a 2.4 Earth radius planet in the habitable zone might require migration or efficient accretion. The presence of a thick atmosphere could also be influenced by the planet's irradiation history. Photoevaporation is stronger close to star, inhabitable zone weaker. Therefore, envelope retention is more likely, unless the planet was initially closer in and later migrated outward, which is less common. Thus, a planet like Kepler 22b might retain an envelope if it captured one. This increases probability of mini-Neptune or volatile-rich state. Yet without mass, the conclusion remains probabilistic. A further constraint is the planet's density distribution. If a planet is volatile-rich, its radius is inflated relative to a rocky planet of same mass. For a given radius, a volatile-rich planet can have lower mass. If Kepler 22b's mass is modest, gravity could be near Earth's. If mass is high, gravity is higher. In both cases, radius suggests some volatile component, but not necessarily. The continuous narrative then allows a deeper dive into atmospheric models for super-Earths and mini-Neptunes. In hydrogen-rich atmospheres, temperatures in a habitable zone can be maintained with less stellar flux due to collision-induced absorption. This can extend habitability outward. But in the habitable zone around sun-like stars, hydrogen atmospheres could make planets warmer than expected. The presence of hydrogen also affects lapse rate, cloud formation, and photochemistry. Hydrogen can reduce CO2 to methane under certain conditions. Methane is a greenhouse gas. The chemical stability of methane depends on UV. In sun-like UV, methane can be destroyed unless replenished. In CO2N2 atmospheres, the familiar greenhouse physics applies. Water vapor feedback can be strong. CO2 can regulate. Cloud can reflect. The carbon silicate cycle can stabilize if geology is active, but super-Earths might have different tectonic regimes: stagnant lid, episodic tectonics, or continuous plate tectonics. Stagnant lid planets can still outgas, but carbon recycling is limited, potentially leading to CO2 buildup or depletion. Episodic tectonics could cause climate swings. Magnetic fields also depend on tectonics and cooling. A stagnant lid planet might cool differently, affecting dynamo. Yet some models show dynamos can persist without plate tectonics if core cooling is sufficient. All these elements tie to the central question because they define whether a planet can remain temperate and retain an atmosphere. Another revisit: stellar flares and coronal mass ejections. For sun-like stars, large flares occur, but less frequently than for M dwarfs. Yet over long times, radiation events can affect atmospheres and surface. A planet with strong magnetic field and thick atmosphere can handle. A planet within atmosphere might be vulnerable. The star's activity decreases with age. If Kepler 22 is older, activity might be lower. Age itself matters for human habitation in another sense. Time allows life to evolve and potentially oxygenate. Earth's oxygenation took billions of years. If a planet is younger, oxygen might be low even if life exists. If older, oxygen might be higher. But oxygenation depends on geological sinks. A planet with different geology might never accumulate oxygen. Therefore, oxygen cannot be assumed. From the standpoint of future human habitats, assuming oxygen is risky. The practical approach is to look for planets with existing oxygen signals, but interpreting those signals is hard. Alternatively, focus on planets with physical conditions that could support terraforming or enclosed habitats. Kepler 22b's distance means it cannot be visited, so it becomes a case study in how remote sensing could evaluate habitability. If a similar planet were found around a nearby star, the same physics would apply, but data would be better. Thus, Kepler 22b is a proxy for an entire search. The narrative continues by deepening the physics of light and spectra. Reflection spectra depend on atmospheric scattering and surface reflectance. Rayleigh scattering makes skies blue on Earth because shorter wavelengths scatter more. On a planet with thicker atmosphere or different composition, sky color changes. But more importantly, Rayleigh scattering affects albedo, cooling the planet. A planet with thick N2 atmosphere might have higher albedo. Clouds raise albedo. Ice raises albedo. Vegetation can create a red edge feature, but this is speculative. Thermal emission spectra reveal temperature, and atmospheric opacity. The planet emits most strongly at wavelengths around 10 microns for Earth-like temperatures. CO2 absorption bands show. Water vapor shows. Measuring emission requires secondary eclipses when the planet passes behind the star, allowing subtraction. For planets in habitable zone, secondary eclipses are rare and shallow due to long periods and small planet-star flux ratios. But around small stars, emission is easier. For sun-like stars, challenging. Therefore, the most accessible temperate planet spectra may come from planets around M dwarfs, but those have other habitability challenges. This creates a tension. The easiest to study are not necessarily the easiest to inhabit. Kepler 22b is around a sun-like star, which might be more favorable for stable habitability, but harder to study. The future human home might be around a sun-like star, but scientific confirmation requires advances. At this point, the narrative can explore the specific physical demands of human habitat. Oxygen, pressure, temperature, radiation, gravity, day length, seasonal variation, and resource availability. Each is a planetary parameter. Oxygen depends on atmosphere and biology. Pressure depends on atmospheric mass and gravity. Temperature depends on insolation and greenhouse. Radiation depends on atmosphere and magnetic field and star. Gravity depends on mass and radius. Day length depends on rotation and tidal interactions. Seasons depend on obliquity and orbit. Resources depend on crust and water. None of these are optional. A planet must satisfy enough of them to be feasible. A planet that fails one might still be used with technology, but the cost rises. Kepler 22b's unknowns mean it cannot be judged as feasible or not, but the exercise of judging it defines the science. Returning to detection again, because the very existence of candidate planets depends on biases, and biases shape what is considered possible. Transit surveys detect planets that align. The geometric probability of transit decreases with orbital distance. Probability star/A. For habitable zone around sun-like star, probability is small, on the order of 0.5%. Therefore, for each detected transiting habitable zone planet, hundreds exist that do not transit. Kepler stared at many stars to overcome this. Thus, the existence of Kepler 22b implies a larger unseen population. Radial velocity surveys detect planets by wobble and are biased toward massive and close planets. Microlensing detects planets by gravitational lensing and is sensitive to planets at a few AU, including cold planets, often far from their stars, and can detect lower mass planets. Direct imaging detects wide-orbit giant planets. Each method samples different parameter space. Habitability requires planets at moderate distances, which are hardest. Therefore, the population of potential homes is inferred statistically. The field moves toward synergy, transit for radius, radial velocity for mass, spectroscopy for atmosphere. Without all three, habitability remains uncertain. Kepler 22b can be revisited as an early example of the synergy's limitations. Transit gave radius and orbit, but mass remains uncertain. This highlights the need for bright targets. Yet the planet remains a key data point in the statistics of habitable zone candidates. As complexity escalates, the narrative can explore interior structure modeling. Given mass and radius, one can model interior layers: iron core, silicate mantle, water layer, gas layer. Equations of state define how materials compress under pressure. For super-Earths, pressure in the mantle could be much higher than Earth's, changing mineral phases and conductivity. This affects convection and dynamo. In high-pressure mantles, viscosity might increase, slowing convection, but temperature might be higher. The interplay determines tectonics. If Kepler 22b is rocky and massive, pressure at core mantle boundary could be significantly higher than Earth's, affecting core composition and melting. A larger core could sustain dynamo longer, or convection could be suppressed. The uncertainty remains, but the principle is that mass and radius connect to deep interior, and deep interior connects to surface habitability. A deeper revisit to carbon cycling. The carbonate-silicate cycle depends on weathering, which depends on temperature and rainfall. Weathering increases with temperature and precipitation, removing CO2 and cooling. Volcanism adds CO2, warming. This negative feedback stabilizes. But on an ocean world, weathering occurs on seafloor basalt, which can still draw down CO2, but the dependence on temperature differs. Seafloor weathering may be less responsive, weakening feedback. Without continents, feedback could be weaker. On a planet with higher gravity, mountain building might differ. Erosion rates might differ, affecting weathering. If gravity is higher, mountains might be lower because rock strength relative to weight limits height. Lower topography could reduce exposed rock area, but increased erosion due to higher rainfall could compensate. Complex. Climate stability therefore depends on details. Water inventory also affects habitability. Too little water yields dry planet. Too much yields ocean world. Dry planets can still be habitable if they have stable water reservoirs and moderate temperatures, perhaps with desert climates. Dry planets might avoid runaway greenhouse because less water vapor, but they might have limited biosphere. For humans, water is essential, but technology can manage. The optimal water inventory for habitability might not match Earth's. Kepler, 22 BS water inventory unknown. The narrative can then incorporate the role of atmospheric pressure in water phase stability. At low pressure, water boils or sublimates. At high pressure, water remains liquid at higher temperatures. Pressure also affects cloud formation and humidity. A planet with slightly higher pressure could have stable oceans at higher temperatures without boiling, but greenhouse might still make it hot. A planet with low pressure might have liquid water only in transient conditions. In a future human habitat, a stable hydrological cycle is advantageous. Rivers and rain distribute water, but hydrological cycle depends on temperature gradients and topography. Returning to orbital parameters, eccentricity and obliquity. A planet with high eccentricity receives variable flux. If oceans and atmosphere are thick, thermal inertia can buffer, but extreme eccentricity can drive freeze-thaw cycles. Obliquity extremes can cause polar regions to receive more insolation than equator, changing climate patterns. The presence of other planets can excite eccentricity through secular interactions. The system's architecture matters. The narrative can remain calm and observational, moving between these constraints like a slow camera orbiting a planet that cannot be seen. At some point, the documentary returns to the central image, a planet's transit, a dip in brightness. That dip is the beginning of everything. From it emerges a radius. From radius emerges a set of possible gravities. From gravity emerges atmospheric retention. From atmosphere emerges climate. From climate emerges surface water. From surface water and geology emerges long-term stability. From stability emerges the possibility of a home. Kepler 22b, as an object, is a reminder that the search for a new home begins not with rockets, but with precision photometry.